Okay, let's get started. I guess the projector's still off, so we'll have to deal with this for now. So I posted a whole bunch of stuff on Slack. I posted homework 2 solutions. I posted homework 4, which we're going to go over in a second. I posted the 2 papers that we're going to read for next week. And I think one other thing, but I don't remember. Yeah, so homework 2s are right here, so feel free to pick them up if you haven't. So homework 3 is obviously due Friday, so any questions about homework 3? Yeah.
For computing the bound for n,
Mm-hmm.
actually, I'll just have something less.
Okay. Okay. Other questions about homework 3? Yeah.
Yes, for question 1, do you want me to perform like someone else did time block A?
So you don't have to be like some exact value times log k, but you could if you wanted to. Just have something on the right-hand side that involves t, k, and v. It should only take like 4 steps to solve it. Yeah.
Last part of the second question. Should we graph what we find, like the formula we find in the question 1, and compare that graph with what we get from our
So I'm not sure what you mean. So let's actually look at homework 3.
Also, how do you lambda 1 results?
Yeah. So we actually talked about lambda equals 1 last time.
Yeah.
So if you plug in lambda equal 1 into this equation, it's the same equation as the one before. So what you would find via your code is the exact same bound, or at least you should. Because the n that you find from question 1 is exactly the same as for question 2, but for lambda equal 1, because they're literally the same equation in that case.
So, do you want us to graph that?
Oh, you want to graph? Yes. I do want to see a lambda equal 1 plot, a lambda equal 2 plot, 3, 4, 5 on the same.
The formula to show that they're the same.
Oh, no. So this is just. So what I'm expecting is a plot like this where you have 5 different bands, I guess.
Yeah.
Which just come from your code. So it's not necessarily related to question 1, but lambda equal 1 is exactly the same n in both cases. I mean, you could just run your code and just plot what you get, but you should get exactly the same number. Other questions about homework 3? Okay, let's talk about homework 4 just a bit. So last time we talked about this one row randomly at a time idea. The only thing that I'm going to ask you to do is just implement it. So just for the first row, just generate a row until you cover at least the expected number of interactions for the first time. And then when you cover that many, then you put that row in and then work with the next row, and then work with the next row until you actually make a covering right at the end. So of course, like different choices at different points are going to lead to different numbers of rows at the very end. So I want you to see what is the range. If you run the same algorithm over and over and over, are we going to get a very tight range on the number of rows or a very wide range? So that's what I want you to do. And I have also some other project ideas. So at this point, you should start thinking about who do you want to work with for your project, what project idea do you want to do, and that sort of thing. So remember that the due date for the proposal, I think, is March 2nd, if I'm not mistaken. Okay, so if it's not March 2nd, look in the syllabus because that's when the deadline is. So make sure to send that in before the deadline. Okay. Any other questions though? So make sure to read the paper for Friday, and are the 2 presenters here? Okay, so cool. So make sure you work together, and we should have a good discussion on Friday. Okay, so let's revisit what we were talking about last time. So we were talking about these greedy methods to make covering arrays, right? Let's go full screen. So we were talking about these greedy methods because the exact methods, which is what we want, are extremely slow in practice. So if we can have a greedy method that doesn't necessarily get the optimal answer, but gets asymptotically the optimal answer, that's good. And hopefully it runs faster. So we talked about some terrible methods first, which are greedy but are slow also. We're going to read about ATeach on Friday, for Friday. Then we talked about the random algorithm, which is we just repeatedly generate one row at a time so that at some point we're going to cover at least the expected number of interactions. So if we have sigma interactions that are still left uncovered, well, the probability of each one being covered in a random row is 1 over v to the t. So the expected number of interactions we will cover is the number that we have times the probability for each one. And because the number has to be an integer, the number of interactions we have to cover is always an integer, then the ceiling is achievable here. Of this number. So that's the expected number of interactions. So we just repeatedly generate a row until we get at least that number, put that row in, and then reevaluate how many interactions are left. And we just keep going until we have no interactions left uncovered. Now we have an array, a covering array. Of course, as you'll see in homework 4, you're not going to get the same number of rows or necessarily a very tight bound on the number of rows you'll get. So it's not a very small range. It can be a quite big range of numbers of rows. So what is often desired is to what is called de-randomize algorithms. So we have a random algorithm that does something, but we want things to be reproducible. So the density algorithm is, or conditional expectation is just a de-randomization of this idea of generating a row randomly and then until you get a good row and then putting it in. It's just a deterministic version of the same algorithm. So what we talked about was we look at a row and we look at each of the entries one at a time and we decide for each interaction left, so like let's just say the interaction is this t right here, we see what is the probability that t will be covered in this row. So then we worked out an example. If we have a row like this, well, the entry in column 3 is a 1, and the entry in column 2 is not fixed yet. So if I just fill in these other 3 entries uniformly at random, then the probability that t is covered is a half, because the entry in column 2 could either be a 0 or 1 independently. So the probability that t is covered is a half. And then what we do is we figure out that probability over all the interactions we have left, add them all up, and just see which one of them, either the 0 being placed there or the 1 placed there, gives us a larger expected number of interactions that we're going to cover. So a larger number of things we're going to cover. So if it happens to be 0, for example, then now if we look at if we fill in these last 2 entries uniformly at random, this t interaction is fixed now in the row. It's already covered. So now it's 100%. So then we reevaluate the probability for each uncovered interaction among these 2 columns and just decide again which one of the values, 0 or 1, will give us a higher expectation of things that we're going to cover. And we just repeat over and over and over until we get a row. And then once you get a row, put it in the array, and then reevaluate the interactions you haven't covered yet, and then repeat. So you can show via this because that you're always getting at least the expectation, you will get the logarithmic bound, because the logarithmic bound came from if we just did the expectation every time. But we're always getting at least the expectation. So therefore, we're always going to get logarithmic in k. So here are some computational results of this. So these are not mine, these are my advisor's results, but it's actually pretty indicative of what's going on. So I should back up. So what is being plotted here is what is the best known covering array number of rows found. So the number of factors, so that's k. So the number, so this is k being plotted on the horizontal axis, and n is being plotted on the vertical axis. So obviously we want to make this plot go as low as possible. So, and it's done logarithmically in k for the x-axis because since we know that the bound is logarithmic in k, we should see a straight line, or something like a straight line, because we're plotting logarithmic in k. So what are these three colors here? So the blue color, that is the best known before density. So if you just look at any possible method or any combination of methods and just see what the best possible thing you can do is, that's what is best known before. And as you might expect, the black line right here is if we include density into the methods. Okay, so the blue line is before density, the black line is after we include density. Then you may think, well, what's that red line underneath? So one of the interesting things is that since we're getting at least the expectation, so we're always doing at least as good as the random method before, what do you think this black line is? Is it better or worse than what the probabilistic method tells us? So the probabilistic method says logarithmic in k, and that is based on doing exactly the expectation every single time. But the density method always does at least as good as the expectation. So what do you think? Do you think the black line is below the probabilistic bound or above it? Hint.
Below.
Yeah, so it's actually below, because we're always doing at least as good as the expectation. So if you plot the probabilistic bound, it would look something like this. So if we plot the probabilistic bound, so the one that you're solving for homework 3, if you just plotted it, it would look like this. So then you may think, okay, well, what's that red line for? So this red line is something that you could do as a project, is a different probabilistic bound. And namely, it's something called the, and I don't know how to pronounce this correctly, the Lovász local lemma. Actually, I'm not sure if it's exactly that method. There's one of two methods it could be, but I'm pretty sure it's that one. So the reason for this bound is that it's always better than the probabilistic bound. So yeah, so it's plotted here because it's just a comparison between here's a method that we know how to actually construct the array, but here is a bound that we absolutely know always works too. So the probabilistic bound says there is a covering array of this size. But of course, the density method clearly shows that we can do better than that. Just because there is a covering array doesn't mean that there isn't a smaller one. So the red line is another bound which says there exists a covering array smaller than this. But we don't know necessarily what the size is. So it's just an indicator to you, well, the blue line is the best that we can possibly do with an explicit method, a method that actually makes the array directly. So the probabilistic bounds say there exists an array, but it doesn't tell you how to make it. So yeah, so it's just a way of visualizing how good the algorithm actually does in practice. It does pretty well in practice because it improved the blue line pretty substantially, but it's still kind of far from the truth. Any questions on that? Yeah.
The x-axis is log k, right?
What's there?
The x-axis?
Yeah, it's logarithmic in k, yeah. Yeah, it doesn't matter what the base is because if we just choose a different base, it would just be a different slope. But if we plotted this long enough, it would look like a straight line. But because the asymptotics are log k. Yes. Other questions? Yeah.
If it's k, how do you get data points between 1 and 2, or 2 and 3?
Oh, so this is logarithmic in base 10. So if we looked at the k right there, that's 10. Yeah, and then so like this point's 10, 9, 8, 7, 6. Yeah, it's a consequence of plotting in log k, but yeah. And you may think, okay, well, what does this mean up here where it says 5 CAs? That means that T, the strength, is 5. So we're looking at 5-way interactions. Well, then you may think, well, okay, well, it starts at 6. Well, why don't you go down to 5? Because 5, we know the answer is just v to the t. Why are you doing 6? So it turns out we were going to talk about this, and I think I have slides about this, but I just decided for sake of time and sanity, we weren't going to talk about it. But the reason why we start at 6 is because of something called an orthogonal array. So there's a construction of what is called an orthogonal array. What that means is it's a covering array that has exactly v to the t rows. So it's as small as it possibly could be. And it turns out with something called a finite field and things working with polynomials over the finite field, what you can do is you can get an extra column out of this if the number of symbols is a prime number or a prime power. So because we have 5, if we have v equal 5 here, because we have 5 symbols, and 5's a prime, we can get 6 columns for free and still have v to the t rows. So that's why it starts at 6 here. If you don't have a prime or a prime power like 10, for example, then you have to start earlier. So you don't get an extra column for free. You have to start at it's a smaller value than that. And that's actually one of the reasons why that one project is listed, although I think someone took it, is the one about whether a covering array with strength 2, 5 columns, and 10 values exists, because 10 is not a prime or a prime power. So we don't have these nice constructions that actually make this covering array with a fairly substantial number of columns. With 10 values, there's no finite field, although I won't get into what that is. There's no nice structure to make the array. So we don't know if one exists, so that's why I put the project out. Okay, yeah, any questions otherwise about this? Because I want to talk about a higher index version of density, which hasn't been published yet. And although if you want to pursue it, you may be the first person to have this published. Okay, so let me talk about higher index. Yeah, so there are some improvements that you can do for the base density method. So let's talk about a higher index version. And I have code for this method that I'm going to give to you so that you can play around with it if you want. Because it's not completely trivial to implement. It took me a while to actually implement it, but it's a fairly easy to understand idea. It's not necessarily easy to implement because it's really difficult to avoid really small details. So there was even one example where I found a difference between using floats and doubles. So if I used a float, it didn't work, but if I used a double, it worked. So there's very fine calculations being happening here. So why do I want to talk about this? So what was the normal density method doing? It was saying that what's the probability that this interaction will be covered in this row that I'm making? What's the probability? And we're just making that calculation over and over and over. That doesn't immediately translate to higher index. So if we have index lambda, for example, and we're trying to build a row R right here, and let's just say we have 6 columns, it doesn't matter though. And so let's just say that we have an interaction T that has, let's just say our index is 2, just for simplicity. And our interaction T has been covered 0 times. Okay, let's just say before this row, it's not been covered at all. Well, what is the probability going to be calculating then? Well, we can't achieve this interaction being covered twice in one row. That's not possible. So we're not really calculating a probability here. So it's the idea of getting at least as good as the expectations not going to work anymore. So we got to think of another idea. So that's one of the reasons why I have you doing that second question on homework 3, where you're calculating the value of n, because there is a way that we can actually achieve this. So the way that we're going to achieve it is like this. So the first step is to calculate n based on the probabilistic method, or just a bound on n. It doesn't actually really matter. And the interesting thing is, it almost doesn't matter what value of n you choose. And I can talk more about that. But you just choose an n that the probabilistic method guarantees, although that's not required either. Just choose a value of n, and then what you do is, as a row is being built, then we're going to calculate the probability that an interaction T will be covered lambda times, and here's the crucial part, if all remaining rows are chosen randomly. And I'll show you code for this. So the normal density method said, what is the probability that this thing that's not being covered currently will become covered in this row? We can't use that here. So what we're doing instead is we're calculating the probability that it will become lambda covered in one way or another in the remaining rows. So just as an example, so let's just say that we have 5 rows that are already built up here. So that means we have n minus 5 rows left to build. So I'll put built here. And then down here, so we have n minus 5 to be built. And then just for sake of, let's just for an example say, let's just say that lambda equals 3 and some interaction t covered 1 time in first 5 rows. So how many more times does it have to be covered? At least. 2 more. Because it's been covered 1 time in the first 5 rows, I need to get to 3 times, and so 2 more. So for this interaction, we're going to, right here, calculate the probability that T is covered twice, 2 times, in n minus 5 rows. But the idea otherwise is exactly the same. You make that probability calculation over for every interaction, you sum them all up, and then you say for each position in the row that you're making, what's the probability it will be covered 1 more time in this row? And then if it is covered 1 more time in this row, then you look at the probability it will be covered the remaining number of times in the other rows. But if it's not covered in this row, then you need 1 more time in the other rows. So just as an example, so suppose that we're building the 6th row right here. And if T has a probability of being covered in this 6th row, then it'll be the probability that it is covered in this row 1 more time. And then it needs to be covered 1 more time in the other rows that haven't been built yet. But there's a probability that this interaction T is not covered in this 6th row. If it isn't covered in this 6th row, then it needs to be covered twice in the remaining rows. Okay? So it's a probability that it is, as we're making this row, then it needs to be covered 1 fewer time in the remaining rows. Otherwise, if it isn't covered in this row, then we look at the probability it'll be covered 1 more time than necessary in the other rows. Okay. It took me several months to actually design this. Do you understand it after 5 minutes of explanation? Yeah.
I don't understand why, if for the 6th row you find that second interaction that you want, and my question is, how come you can't just? Because you said that you want to see the probability of that interaction appearing again in that 6th row and appearing once more in the rest.
So,
how come you can't just say the interaction appears? Why can't you just see the probability of that interaction appearing just once more in the remaining rows?
So remember that an interaction has columns and values.
Yeah.
So an interaction can only appear at most 1 time in each row.
Yeah.
So let's actually look at a concrete example, or concrete, I guess. So let's just say that we have, here's a row that we want to make. And let's just say it has something like this. So I guess 6 columns again. And let's just say our interaction T, our columns are 2 and 3, just like before, and then values are 0 and 1. Then, and let's just say covered once or 1 time before this row. And our target index is 3, just like before. So it was covered one time before this row, and we need to cover it at least twice in maybe one time in this row and then one time later, or 0 times in this row and twice later. So, well, what can happen? So what we need to do, so this is getting more into the details. So let's say we're looking at this entry and we want to fix it to a value. Well, it could either be a 0 or a 1. So what we need to do is, well, suppose that it's a 0. Let's temporarily assign a 0 here. So I'm going to assign a 0 there. Is T covered in this row now? Yeah, because in column 2 we have 0, column 3 we have a 1, so it's covered in this row. So let's just assume column 2 has a 0. Then we calculate the probability that T is covered one more time in remaining rows. So all the rows down here. So this is on the assumption that we're going to put a 0 there. If we're putting a 0 there, then we just look at the probability that it's covered one more time in the remaining rows. And then we just sum those probabilities over all the interactions we're interested in. And then it could be that putting a 1 here is better. It might be better if we put a 1 there. So let's say we want to put let's just say I don't want a 0 there. I want a 1 in that position. Well, is T possible to be covered in this row? No, because in those positions we have a 1, 1, which is not the interaction. So for that reason, how many times must T be covered in the remaining rows?
Twice.
Yeah, twice. Because it's not covered in this row, it's been covered once before, it needs to be covered 2 more times, so we look at the probability. So if we assume call 2 has a 1, then same thing, that T is covered twice in the remaining rows. Okay, so we just make these calculations over and over. Then we see, does 0 have so the interesting thing here is, what did the density method do? We were always getting at least the expected number of things that are covered. Here we're doing something different because we're looking at the probability that it will be covered, but it turns out that it's better to consider the probability that it's not covered in the remaining rows. So then what we're trying to do is we're trying to minimize the number of uncovered interactions left uncovered after all rows are done. So once all the rows are completed, then we want to minimize the expected number of interactions left uncovered once all rows are complete. So that's why we did that first step at the top. We chose an n at the start so that there exists a covering array. And then what we do is when we're making a row, we just see as long as the expectation is always strictly less than 1, then there is a way to fill out the remaining rows probabilistically. And since we always do better than the expectation, we always will achieve the number of rows that we have, or smaller. But we always will be able to achieve the goal, to fill out all the rows and have no interactions left uncovered. So let me actually show you some code. Unfortunately, it doesn't run. And there's a very good reason for that. So let me actually walk you through some of this code. I'll clean it up and I'll submit it to you so that you can actually run it and then test things yourself after homework 3 is due. Because it has code that'll calculate the n for you. So it sounds like it looks like a lot of code, but it actually isn't. So this is actually copied and pasted from some of the work for the paper I just submitted. So that's one of the reasons why it doesn't actually run. So it was reliant on other code in order for it to work, which is not here. So the basic idea is exactly what we were saying. So we find the smallest number of rows that work, and then I don't know necessarily if we're going to get it within n rows or maybe even smaller. So I just put a while true loop here. If we ever get to a point, maybe fewer than n rows, where we have if we have every interaction fully covered, so everything covered lambda times, then I just stop, which is right here. So this t sets left thing is saying, I'm going to get every interaction if the number of times it's covered is less than the index that I want. So if it's not the index I want, at least, then I want to consider that interaction. And if there are none left, then we stop. So then now, if there is an interaction left, I'm going to build a row to actually make it. So what we do is exactly like the original density method. We look at each column one at a time. Doesn't really matter what the order is. Here I just do it in normal order. Then what I do is I create a dictionary here, and that goes back to the float versus double thing. So what I do here is, for each of the values that can be assigned to this position, this column, for each of the v values, I'm going to store what the expectation is. And then I just look at the expectations at the end and pick the value that has the smallest one. So basically, I'm just making a dictionary. I'm going to have keys and values. I want to pick the key that has the smallest value. So a natural, easy problem to do. So then I loop over all possible values that can be assigned there. Then I make an expectations list. There's a good reason for that. It has to do with, have you ever had the experience of you add two floating point numbers, but if you add them in the other way, they don't give the same value? That happens here. So what I did was I made a list of each of the expectation calculations. I sorted the lists, and then I added the things in that order. So by sorting the list, I always get the exact same thing every time. And so there are no numerical calculation issues there. So then what I do here, I actually shuffle randomly the t-sets. That was just for an experiment. You don't have to shuffle the things here. I look at each interaction. Then I get the columns and values out of the interaction. Then what I do here is, so it's actually a computational optimization. So suppose, for example, that we had this example before. So right here. So we had 0, 1 there, but let's just say, for sake of argument, that it's not filled. But let's, for example, assume that I'm looking at the 5th column here. Oh, sorry. I need to get better at that. Yeah, so let's just say we have this situation where we have a partially filled row, and we're looking at the 5th column. And we got to decide whether a 0 or a 1 fits. So does the interaction T that involves columns 2 and 3 have anything to do with column 5? No. So what we can do to optimize this is, let's look at any interaction that involves column 5. I don't care about any other ones. So as long as we involve column 5, then that's all that matters. So in terms of the code here, I check if the column we're observing is in the interaction sets of columns. If it is, then we need to make the probability calculation. Otherwise, then we just observe whether or not it's possible to cover this interaction. So, like for example, so if we're looking at that column 5 again, and for example, if there was a 0 here, then interaction T is covered in this row with 100% certainty. And if instead it was a 1 there, then it's covered not at all with 100% certainty. So it's definitely not covered if there was a 1 there. So we just observe the probability that it is covered. So that's where the probability equals 0 there. And then this is just the calculation of the probability of having the right value in every column not fixed yet. Yeah, and the calculation over here is similar, but there is a small optimization here. So you notice right here, if I can make this a little bigger, what I'm doing is I'm looking at the values in the row that are fixed right now, but with the addition of if I fix this column to this value, then I looked at this, then I'll see what happens. Then okay, yeah, that's a different thing. But basically what I'm doing is I'm just seeing if I looked at the fixed things in the column as well as putting this new value in and seeing what happens. Then what I do is this really weird calculation right here, but I'll go over it. It's actually very, very simple. So I'm going to append onto this list the probability that we're going to cover everything. So it looks terrible, but the basic idea is the probability that this interaction will be covered times the probability that it will be covered in the remaining rows one fewer time, which is where this 2 comes from. You may say, well, one more time 2, what does that have anything to do with it? There's a reason for that. Then we look at the probability otherwise that it's not covered in this row, and it needs to be covered one more time in the remaining rows. So then you may think, okay, what is this G function? This G function is exactly what, or I guess up to one difference, but basically the idea of doing the calculation that you're going to be doing in homework 3, where you're just you're doing the k choose t times v to the t times that sum thing. Well, here's the sum. So you're going over all possible choices of I. You do the number of rows, basically choose I, times that probability to the I, times 1 minus p to the n minus I, basically. And that's what I'm doing throughout this entire thing. Then for this particular value, the expectation is just the sum of the probabilities, which is what I'm doing here. Then the best value that I could place in this position is the key in the dictionary, the value that has the smallest expectation, because the expectation in this case is the expected number of interactions left uncovered at the very end, and I want to minimize that. And then once I pick the best value, I put it in the row, and then once the row is entirely complete, once I look at every single column, then I append the entire row. And the simple calculation down here is, if it's actually covered in this row, then I'm going to increment the number of times it's been covered. So if it appears in this row, then I'm going to add 1 to the number of times it's been seen. And that's basically it, other than this one thing down here. Any questions about the high-level idea behind it? So one thing that relates to these last two lines is something that I think is really worth looking into and is a great project idea. So here's what could happen. So let's look at the very first row. The first row. Well, does it matter what row we choose the first time? No. And the reason for that is, remember, we can permute the values in the columns to get a row of all zeros. So we can, without loss of generality, have a row of all zeros. And in fact, any row you choose here is as good as any other row so far. So it doesn't matter which row you choose first. So for that reason, if you look at the expected number of uncovered things at the end, before you add this row and after, it substantially drops. So if you make a plot of what happens, so like the expectation and the number of rows added, and let's just say the expectation of 1's right there, well, at the very beginning, oh, sorry, I need to get better at that. Yeah, so if we make a simple plot here, well, at the very beginning, we always choose an expectation that's strictly less than 1 at the very beginning when there are no rows. So it'll be something there. But if you just apply this, this density algorithm over and over and over and keep adding rows, well, the expectation is always going to drop, it turns out in practice. So it's not just that it's strictly less than 1, but it always decreases like this. So what you can do is, well, if you can determine, say like right here, after you made like 1 or 2 rows or something, if we can reduce the estimate on n, then as long as the expectation still remains less than 1, and I can reduce the estimate n on the rows, then we can still complete the array in exactly the same way. So if, for example, we re-estimate or recalculate n based on the same formula that you did at the very beginning, then what you do is you increase the expectation to just under 1, but the estimate on the number of rows went down. And then what will happen is you make a few more rows, it goes down, and then you re-estimate, and it goes up again, and then down, up, down. And then as long as the expectation remains less than 1, you can always complete the array. And you'll get a better estimate every single time. But one thing that might be worth looking into is, what if I started the estimate higher than 1? So if I started it less than 1, that guarantees I'll finish it. If I start it larger than 1, it doesn't guarantee I'll finish it, but in practice I still do. So in fact, what I could do is I can look at higher and higher choices of the expectation, meaning a smaller number of rows, but I don't necessarily guarantee I'll make the array. So what a good project idea would be, in this case, is look at different initial expectation choices for n. And what I've seen on a related thing, not this, but on a related thing, is that different choices of the expectation at the beginning can lead to a smaller number of rows or larger. So it actually, there isn't like a settled thing, like if you're within this range, that's the best you can do. It's just that there are different outcomes depending on the expectation you choose. And there doesn't seem to be a clear answer here. So it would be a really good idea to actually look into this and see. I think that's all we have for today. So are there any questions? Great. I'll see you on Friday for a paper discussion.